Hi, my name is Gabrielle Heuler, and my project is on nylon, and I'll be discussing its structure, mechanical properties, and applications. Nylon is a synthetic polymer, so it is a large molecule consisting of many identical smaller molecules called monomers that are bonded together. The monomers of nylon form amide bonds, so it is specifically a polyamide. This right here is a representation of an amide bond. As you can see, the carbon is from a carbonyl group, and it's bonded to a nitrogen from an amine group. There are two ways nylon can be synthesized. The first is condensation polymerization, where diamine and dicarboxylic acid repeatedly form amide bonds. Then we have ring opening polymerization, where identical ring compounds that contain amide bonds open and the carbon chains attach to each other. Some examples of nylon include nylon 6,6, which is synthesized by condensation polymerization. It has two monomers, hexandioic acid, which is a 6-carbon compound with carboxylic acids on either end, and 1,6-aminohexane, which is a 6-carbon compound with amine groups on either end. As you can see, the two monomers line up with each other, and the amide bond is formed, and a water molecule is also produced for each amide bond, which is why it is classified as a condensation polymerization. Another example is nylon 6, which is made from the ring caprolactam, which contains an amide bond and can open and react with each other. So the red atom is oxygen and the blue atom is nitrogen. And you can think of this as when the caprolactam ring opens, and now this monomer is ready to become part of the polymer. And obviously, when it's part of the polymer, this nitrogen would also be bonded with another carbon chain. And then this carbon at the end too, one of these hydrogen would actually be a nitrogen from another monomer. So nylon forms long linear chains that are held together by hydrogen bonding. As you can see, the hydrogen bonded to the electronegative nitrogen in the amide bond of one chain can form a hydrogen bond with an oxygen in another chain. Because nylon is long and linear, it is easy for many chains to line up with each other and form an extensive amount of hydrogen bonds. As this is the strongest intermolecular force, this makes nylon strong and significantly impacts its mechanical properties, which I will discuss soon. Lastly, nylon is semicrystalline, which means that it contains areas where atoms are regularly packed or crystalline, and also disordered or amorphous. In solid nylon, 20 to 30% of the atoms are in crystalline structure, and when nylon is drawn into fibers, it is mostly crystalline. And this is just a representation of crystalline nylon. And as you can see, the hydrogen and the oxygens form hydrogen bonds with each other. For its mechanical properties, nylon is a thermoplastic, so at high temperatures, higher than its melting point, it becomes a viscous liquid that can be molded. The high temperatures break the hydrogen bonds between the chains, which allows nylon to be plastically deformed. Nylon also has high tensile strength, which means it can be stretched using a high load and not break. Ductility is a measure of how much a material will stretch until failure, so it is directly related to tensile strength. And since nylon has a high tensile strength, it will be ductile as well. Nylon also has high toughness, so it is more likely to undergo plastic deformation than fracturing because it can absorb energy when stress is applied. And nylon's low coefficient of friction means that it is able to move against materials without damaging its structure, which makes it durable. A high degree of crystallinity increases stiffness, strength, and toughness. When nylon is more amorphous, it is more elastic. From this list of properties, you can see nylon has a high tensile strength and a high melting point. Nylon has many applications in many industries because it can be used as a moving part due to its durability. It can receive tensile stress and impacts, and it can be used in a function where it is heated because of its high melting point. So these are just a few examples of the products that contain nylon, but I want to focus on nylon's application in 3D printing. Nylon is widely used in 3D printing because it is a thermoplastic, and 3D printers use heat to manipulate the material into the desired shape. And I'm going to discuss 3 types of 3D printing that extensively use nylon. First, we have fused deposition modeling, which first heats the material to a molten state and then deposits successive layers on the build platform to produce a model. And this is a picture of an FDM printer, and as you can see, the extruder is where the material will come out of and then be added onto the heated build plate. Then we have multi-jet fusion, and this type of 3D printing actually uses nylon in powder form. So a thin layer of powder would first be heated on the print bed, and then a fusing agent would be applied to the target areas, and this will fuse the powder into the desired shape. A detailing agent is also applied to the outside, as you can see, to ensure the edges are clean. And then lastly, an infrared heat source will activate the fusing agent to fuse the powder together. Lastly, we have selective laser sintering. This process also uses nylon in the powdered form, which is in this area where the printed part is at 4, and the laser, which is number 6, will scan the cross section and apply heat to fuse the powder together, and each layer is made and then lowered into the build chamber, which is number 2, until the part is finished. There are some issues with nylon in 3D printing, and the first one is that nylon is hygroscopic. So if we go back to the table of properties, we can see that its moisture absorption is up to 2.5%. So nylon absorbs water, which is an issue because it undermines dimensional stability and strength. And when nylon is wet and it's heated during 3D printing, the water will evaporate, which will create holes in the structure and make it not functional. The solution to this is to print in a dry and enclosed environment. So for example, for FDM, it is in an enclosure, and if the environment is dry, then you won't have any issues. Also, we have warping issues with nylon, and this is due to uneven cooling on the build plate, which causes layers to not adhere to the plate properly and distort. But the solution to this is a heated print bed.